JWST just spotted Milky Way scale galaxies only 500 million years old. That means our growth timeline is off, not the Big Bang. Picture red smudges that look tiny, yet weigh billions of suns. Their light left when the universe was a toddler. Astronomers expected baby sparks, not mature cities of stars. So what's going on and why were scientists worried? Quick answer: things got big fast and we need new rules. Tonight we trace how those giants appeared so early. Zoom into a faint ember glowing in a velvet black sea. Astronomers tagged it at redshift 13, which means very early. In plain words, we are seeing it 320 million years after origin. That timing matters because building big structures should take far longer. Gravity needs time to pull gas together, then light up stars. Dense clumps merge, and feedback blows much gas back out. The net growth should be steady, not explosive. Yet JWST photographed systems with mature stellar populations and dusty halos. Some look disk-like, with ordered rotation in their starlight. One team measured stellar masses near 10 billion suns at redshift 11. Another saw star formation rates over 100 suns each year. Those are city-scale factories, running before galaxies should organize. Here is the working definition of two early giants. They are galaxies exceeding about 1 billion solar masses before 500 million years. They also show relatively red colors from aged stars or dust. The fear was clear because our models predicted much smaller seeds. Quick check: compare to the Milky Way at 1 trillion solar masses. These youngsters are 100 times smaller, yet astonishingly mature. Their stars show bomber breaks, which signal populations older than a burst. Some spectra even hint at oxygen lines, implying quick chemical enrichment. Numbers like these force new timelines for the first heavy elements. Bottom line, JWST found galaxies that look grown when cosmic time was short. Start with a patch of sky, seemingly empty and quiet. JWST stares for many hours, gathering whispers of red light. Space expansion stretches ultraviolet light into the near-infrared bands. That stretch is called redshift, and it acts like a distance clock. It matters because color patterns reveal when a galaxy first shone. The method is simple to state, but painstaking to prove. Light shortward of hydrogen's Lyman break vanishes, absorbed by neutral gas. So a galaxy drops out of bluer filters and brightens redward. Astronomers fit templates to those colors and estimate a redshift. Then they chase confirmation with NIRS-spec, splitting light into fine spectral lines. A crisp emission peak nails the distance and clears imposters. Actions chain together: image, fit, select, and then measure precisely. Example in real terms: think of JWST targets in Good South. Several objects showed dropouts consistent with redshift between 10 and 14. Follow-up spectroscopy found lines matching that early epoch within uncertainties. Exposure times ran for tens of hours to capture enough photons. The signal is tiny, but JWST's mirrors are exquisitely cold. That keeps thermal glow low and boosts sensitivity by design. A rule of thumb helps: more filters mean safer photometric guesses, but only a spectral line closes the case with confidence. Gravitational lensing can imitate brightness, so teams map cluster mass. Careful lens models prevent overestimating size and mass by magnification. Net result: the technique isolates truly ancient light, not local lookalikes. Now check the traps that can trick even careful eyes. A nearby galaxy shrouded in dust can mimic a high redshift color. That imposter vanishes in blue filters and glows in red. The definition of an interloper is simple: a wrong distance lookalike. It matters because a few misfits can inflate the early census. Teams fight this with deeper imaging and mid-infrared constraints. Thermal dust peaks betray closer objects once you sample enough wavelengths. Spectra settle arguments by revealing rest frame optical lines where expected. Another trap hides in gravitational lensing by foreground clusters. Magnification can turn a modest dwarf into a fake giant. Mechanically, you correct that by reconstructing the lens mass map carefully. Uncertainties remain, especially near critical curves of extreme magnification. A third pitfall sits inside stellar population models and priors. Assume older stars, and you infer higher masses from red colors. Assume a top-heavy stellar mix, and luminosity jumps without mass. Astronomers bracket these possibilities and publish ranges rather than points. Example in numbers: one early colossal galaxy dropped by a factor 5. Spectroscopy showed it was closer, and lensing had boosted the light. Others held firm, staying near several billion solar masses at redshift 11. The guardrails are improving, but claims still carry error bars. So the picture is, some giants shrink away, but many remain hefty. You can feel the tension because a timeline holds the universe together. The concept at stake is hierarchical growth in lambdictum cosmology. In plain words, small things form first, then merge into big structures. That expectation matters because it underpins simulations and reionization forecasts. If big galaxies appear too soon, feedback must be weaker or delayed. Star formation would need to be wildly efficient inside early dark halos. Gas cooling would have to outrun explosions, winds, and radiation pressure. Alternatively, dark matter behavior could differ on very small scales. Most researchers look first to astrophysics, not a new gravity recipe. Mechanically, you tweak star formation efficiencies and feedback coupling in models. You test top-heavy initial stellar masses, which speed enrichment and light. You add bursty accretion histories and reduce time lost to winds. Then you compare Mach colors and sizes to JWST catalogs directly. Example, simulations like Fire, TNG, and Renaissance were quickly retuned. Higher efficiency runs produced billion solar mass galaxies by 400 million years. They still needed periods of low feedback to sustain gas densities. The reionization timeline also shifts because more stars mean more photons. Ionized bubbles would grow faster, reaching significant fractions by redshift 8. Radio arrays can test that with the global 21-centimeter background. Bottom line, the fear was speed. Nature may build earlier and harder. Open the spectrum and the story sharpens into stacked bright spikes. A galaxy is defined here by its fingerprints, the nebular emission lines. Those spikes matter because they expose chemistry, age, and star formation. JWST catches rest frame optical lines redshifted into the infrared bands. You see hydrogen bomber lines and oxygen at 5007 nanometers. The ratios trace temperature and the metallicity of gas clouds precisely. Mechanically, astronomers fit photoionization models to the line strengths and shapes. High equivalent widths point to young, massive stars flooding regions with photons. A strong bomber break hints that older stars already built up. Dust absorbs blue light, then shines warm in the mid-infrared. MIRI detects that glow, revealing grains forged in early supernovae. Example numbers help: gas metallicities near 10% of solar at redshift 10. Dust masses approaching 1 million suns within a few hundred million years. Star formation rates inferred from H-alpha over 100 suns yearly. Line widths of a few hundred kilometers per second, implying rotation. Overlay the facts: enrichment started fast and assembly was surprisingly organized. Quick caution: line visibility can be dimmed by neutral hydrogen outside. That makes Lyman alpha rare, even when other lines are clear. Net result: spectra confirm real distances and reveal mature ingredients very early. Now tilt toward the cores, where gravity writes stranger stories. An active galactic nucleus is simply a feeding supermassive black hole. That matters because its mass growth tracks how fast galaxies evolve. JWST sees hot dust around accreting holes in the mid-infrared. It also sees broad emission lines, smeared by orbital speeds near light. Those are clean AGN signposts, even in young compact systems. Mechanically, you estimate black hole mass from line widths and luminosity. You compare the power to the Eddington limit, which throttles accretion. If power brushes that ceiling, doubling time is tens of millions. Several cycles fit before 700 million years if fueling persists. A bolder route starts heavier, with direct collapse seed black holes. Those seeds could weigh 100,000 suns from birth. They skip the long build from tiny stellar remnants entirely. Super Eddington phases can also sprint if geometry funnels radiation away. Example catalog points: quasars at redshift 7 carry billion solar mass holes. JWST adds candidates beyond redshift 10 with mid-infrared excesses. Some show compact sizes under 500 parsecs, implying dense centers. Others reveal outflows clocked at thousands of kilometers per second. The numbers still carry uncertainties, but the trend is daunting. Bottom line: central black holes grew fast, maybe from a head start. Swing the view to a galaxy cluster, glassing space like a lens. Foreground mass bends light paths, stretching background galaxies into elegant arcs. That bending defines gravitational lensing, a natural telescope set by gravity. It matters here because lensing can both help and confuse counts. Magnification lifts faint galaxies above detection limits, expanding the sample, but it also distorts sizes and muddies true luminosities without models. Mechanically, teams build mass maps from cluster member motions and arc geometry. They run ray tracing to recover source positions and magnification factors. Then they correct photometry and derive masses with those factors applied. Example, an arc behind Abel clusters gained brightness by a factor 8. Its apparent size shrank after corrections, along with inferred stellar mass. Several early giants near clusters stepped down similarly by 2 or 3. Others away from lenses kept their hefty numbers after scrutiny. A quick guide helps. If you see sharp arcs, treat sizes suspiciously. Use unlensed deep fields to cross-check extreme results for balance. This keeps the census honest without discarding gold from the pan. What to remember, lensing refines the list, but the heavyweights persist. Project forward from these numbers and the consequences stack quickly. Reionization is simply the era when ultraviolet light ionized cosmic hydrogen. That epoch matters because it sets when the universe turned transparent. More early stars mean more ionizing photons and faster bubble growth. Escape fractions must be higher, or galaxies must be more numerous. Mechanically, models now adjust star formation histories to match JWST counts. They fold in dust to avoid overproducing visible light at once. They also track feedback loops, which regulate bursts and quiet spells. Predictions spill into tests with radio arrays listening for 21-centimeter signals. Instruments like Hera, LOFAR, and SCA map neutral hydrogen by redshift. Their power spectra constrain how patchy reionization was across the sky. Cross-correlating with JWST positions can localize growing ionized regions. Example forecast, ionized fractions near 50% by redshift 8 look plausible. Ionizing photon budgets exceed earlier estimates by factors of 2. Stellar metallicities climb faster, which shifts supernova rates and dusk growth. Black hole feedback ignites sooner, changing gas cooling in small halos. Tiny test, can we find population 3-star signatures this year? Look for extremely blue slopes and no metal lines in spectra. Final thought, early giants mean earlier starts, not a broken beginning. We began with a shock, adult-sized galaxies in a toddler universe. The clear takeaway is simple, growth kicked off faster than expected. We are updating the playbook, not discarding the Big Bang. JWST gave us clean eyes in the right wavelengths and time. We now know metals, dust, and dense cores appeared with startling speed. Black holes found fuel fast and may have started bigger. Lensing sharpened the counts, yet many heavyweights still stand tall. Over the next seasons, spectra and radio maps will tighten timelines. I'll bring you the wins, the walkbacks, and the weird outliers. If you want that ride without the hype, stick around here. Tap subscribe so you catch the next deep space chapter when it drops.